Intermolecular forces. Here we're talking about the forces that occur between two molecules. Intramolecular forces would be within just one molecule. So what makes up one molecule? Well, you have the bonds, and then you could also have the distribution of electrons, which would give dipoles, partial charges, and those such things. But when you're talking between two molecules, that would be with an ER, intermolecular forces. So you have, for example, one water molecule, another water molecule. Are they attracted? Are they repelled? Do they have to be oriented correctly? How strong is the attraction? Could it be a third one coming in? All of those type of considerations is what we're talking about. Now, within one molecule, you've got your bonds, which are typically ionic or covalent, right? And those are pretty strong. That's why molecules don't just fly apart, right? In the atoms, I mean, very strong forces that keep those together. Between two molecules, those forces are typically considerably weaker, about 25 times weaker, in fact. And here you see in my notes here, typical bond might be in the order of 430 kilojoules, whereas a weak interaction between two molecules, 17-ish kilojoules. So you have weak and strong forces that are all governing this. And we're talking about just the weak ones in this chapter, the intermolecular forces. Now, we already thought about this a little bit when we talked about different phases. Way back, I think in chapter 1 it was, comparing solids to liquids to gases. We have, again, the consideration of intermolecular forces. And in a solid, like here in the figure here, all the molecules are touching. They're locked into place, so they form a crystal. They can vibrate a little, maybe they can stretch just a hair, that kind of thing, but they're locked into place. And so the forces between them are intact, and they're holding those molecules in that arrangement. With a liquid, they're still more or less touching, but you've given them enough energy, enough kinetic energy, where they were able to break free of some of those intermolecular forces, and so now they're not locked into place anymore. Now they're sliding past each other, and they can flow, and that's why, if I take a solid hunk of rock or whatever and I throw it in a beaker, it just tumbles around, and I could pour the whole rock out, but it stays in form. But if liquid, take water or something like that, of course it flows and it conforms to the shape of the container. That's because those molecules, again, can slide past each other. But there are still forces holding them together. It's not like they just slide and go off or something like that. They're still held together. In a gas, we finally give them even more energy. We give them even more kinetic energy, so that now they can totally break free of those forces, and they're just whizzing around on their own. They're bouncing off the walls, they're bouncing off each other once in a while, but we don't have any forces that are actually strong enough to hold them together because they've got so much kinetic energy in a gas. Now, we talked about a gas in a previous chapter, and because these molecules are separated in a gas, there are, to all practical purposes, no intermolecular forces holding them together. Right? They're each individual, and again, they're flying around. So we've already considered that, PV equals nRT, all of that. Liquids and solids, however, strongly depend on those intermolecular forces because they are touched and they do experience them. And so that's what we're looking at in this case. Collectively, if you look at all of the forces that are holding two molecules together, those are called van der Waals forces. Van der Waals right there. Right? Whether it's an ionic, which makes ionic bonds, that's not really what we're talking about this chapter, but anything else, weak, strong, whether it's some kind of a charge or whatever the force is that's holding those things together, van der Waals forces. These are all these weak forces that we're talking about that control these things. And you can separate them into roughly three categories. The first category of van der Waals forces are the London dispersion forces. Now sometimes you'll hear these be called just London forces, or sometimes just dispersion forces. It's all good. London dispersion forces. Okay? First of all, every molecule out there has these. Second of all, these are the weakest of all of the van der Waals. They're not strong at all, but every molecule has them. And they are due to the fact that the electrons, let's just take one molecule first, the electrons in that molecule, the bonds and the lone pairs, they're all waves really, right? And so they're distributed around this molecule, and they're not stationary, they're in constant motion, they have energy, right? And so just like the waves of water, say in a lake or in the ocean, sometimes they rise and sometimes they fall. Well, the same things are happening with these electrons going around this molecule. Right? So sometimes it'll be a little higher on one side, lower on the other, and then it'll change, it'll go higher on the other side. They're in constant motion. Well, if I have something that's, say, nonpolar to start with, so the bonds are nonpolar or they cancel each other out due to the geometry. You got a nonpolar molecule, but these electrons are in motion. Well, every so often, just by statistical probabilities, you'll get them piling up on one side and not piling up on the other, so you have a little dipole form, a little teeny partial positive and a little teeny partial negative on one side to the other. Then you give it time, that'll flatten back out, and maybe it'll form in a different direction. So you've got all these partial charges forming these little teeny dipoles. It's a random thing, and they're temporary. They appear and they disappear. But if I've got two molecules and one of them forms this little dipole, well, the partial positive part of it is going to affect the electrons of the neighboring molecule, repelling them. Partial negative, it's going to repel them, it's going to push them down, and so you're going to actually induce a dipole in the neighbor molecule in the opposite direction. So if this is partial negative to positive, this is going to be partial positive, partial negative, and then they'll attract. You get a weak attraction, but of course give it just a little bit of time and that'll disappear, and so that one will disappear and they'll go away again. Right? So these temporary little dipoles that form attractions between one molecule to the next. That's what we call London dispersion forces. Here's a little a little diagram figure from the textbook showing these again, temporary dipoles where you have partial positive, partial negative. They're showing in blue, the partial negative, and so it induces a dipole in the neighboring molecule, and you get this weak, small attractive force. Every molecule does this because every molecule has electrons. But the question is, well, are they equal in attraction? Are they equal in force for every molecule? And the answer is no. Some molecules are easier to induce a dipole. Some molecules form stronger temporary dipoles than others, and it more or less has to do with their size. The larger the atom, the larger the molecule, the more electrons it has, the more surface area it has, and the more possibility to make and induce dipoles. All right, so therefore, the larger the atom and or molecule, the stronger the London dispersion forces usually are. Now here's a table showing melting and boiling points of the different halogens. So fluorine, F2, chlorine, Cl2, bromine, iodine, acetine. All right, molecular mass, yep, it's getting bigger and bigger and bigger, so we're going to larger and larger atoms, larger and larger molecules here. All right, here's the radius, just the size of them. All right, look at the melting points. This is a measure of the attractive forces from one molecule to other. See, if I've got these two molecules and they're strongly held together, then it's going to take a lot more energy to rip them apart. That is to say, I'm going to have to get them to a lot higher temperature, and so their melting point is going to be higher. If they're weakly held together, I'm not going to have to get them so hot before they come apart. They'll have a lower melting point. Right? Same thing with the boiling point, exactly same idea. And so you look at these, as I get to larger, go down here, this column, larger and larger molecules, the melting point increases. It goes higher and higher. Why? That must mean they're held together stronger. Why would they be held together stronger? Because they have stronger London dispersion forces. Okay. Now, these are all completely nonpolar molecules, but remember, and so there's no other force that interferes with these. We can generally attribute this trend to London dispersion forces, but remember, every molecule does have London dispersion forces out there. A second factor which can affect how strong these London dispersion forces are is the shape. The shape of the molecule, and especially the surface area that's available for contact. So if I have two like sphere-like molecules and I go to contact them so I can induce a dipole, they might not have a whole lot of area, just a little bit there that they actually contact. As opposed to, let's say I have long, thin molecules and I go to bring those guys together. Well, now I've got all this area between these two molecules, and I'll have a lot more possibility for London dispersion type attraction. And so, point in case here, here are three molecules. They are all C5H2. C5H2. The first one's called neopentane. These are organic molecules, okay? Neopentane, the next one isopentane, the third one N-pentane. Right? They're all C5H2, it's just they're connected differently. If I actually showed you that bonding structure, which let me just do that, I'll add it right underneath here. Neopentane has a carbon right in the middle, and then it's surrounded by other 4 carbons. So there's those 5 carbons, and then each one of these has 3 carbons attached to it. They're tetrahedral, so there's 4 total bonds, and so you can see that's C5H12. Isopentane has actually 4 carbons in a row with the last carbon coming up like that. And again, you can distribute hydrogens around there so everything has a tetrahedral. And so C3 or H3, H3, H3. This one actually has 2 hydrogens, one up and down, and this one would have 1. That's a grand total of 12 hydrogens again. N-pentane, they're all in a straight row. All right, and so in H3, and you got an H and an H, an H and an H. This isn't critical, but I just want to show you the full case here. All right, and so I've got these all exactly the same size molecules, exactly the same mass. Same number of carbons, same number of hydrogens, it's just they're connected a little differently, which gives them different shapes. This one over here, the neopentane, is definitely tetrahedral, kind of spherical shaped. And here's a space-filling model of what that would look like. Kind of looks like a lumpy ball. Right? Whereas in the isopentane, it's more elongated, and it's got this one coming out and on the side, and so not quite so spherical. This one, long, thin rod. And so I think about, well, what kind of London dispersion forces would be from one molecule to the next? What's going to attract there? I think it's pretty clear that the ball shape, the spherical shaped ones, are not going to have as much surface area contact as like the long, skinny N-pentane one does. And the one here, well, somewhere in the middle. And sure enough, look at the boiling points down at the bottom of this figure, 9.5, 27, 36. This one has the highest boiling point. That is to say, it takes the most energy to break those molecules apart, like that. Why? Because there must be some stronger attraction between them. This one has more London dispersion forces, a stronger attraction, because it's got the surface area that allows for more interaction from one molecule to the other, where these, because of the shape, not as much. And these guys are right in the middle. All right, so the size and the shape are the 2 main things that are going to affect London dispersion forces. All right, that's the first of the 3. The second van der Waals type forces to consider are dipole-dipoles. Dipole-dipoles are, again, an attraction from one molecule to the next. It's an intermolecular force, but it's with polar molecules. All right, so you go back to the geometry of the molecules. Maybe you have polar bonds, but they don't cancel each other because of the geometry and the shape and the direction of them. Right, so it has a net dipole for the whole molecule. So this molecule sitting here, it's got a partial positive side and a partial negative side, and it's got a dipole in it. They are not temporary dipoles like we saw before. Right? These are permanent dipoles. The molecules are built that way because of the geometry. And so they're going to see a neighboring molecule, partial positive, partial negative, same thing, and they're going to flip and interact to line up their partial negative and partial positive with each other. There's 2 different ways they could do this. They can kind of do it like nose to nose kind of a thing here, where I've got this dipole here on the partial negative side aligns with the partial positive, or they can do it kind of how I was describing just a second ago, where one flips and they do it, kind of got a double interaction going there. Either way, this is a dipole sort of interaction. Partial positives with partial negatives, they're going to attract. And they're going to be stronger than the London dispersion forces because, again, these are permanent dipoles. They don't vanish. They don't go away. Right? So they're stronger. They're longer lasting. In fact, they're permanent. That's how long lasting they are. And so it's going to be a step up as far as the strength. If you've got dipole-dipole interactions, that is to say if you have polar molecules, the attraction between them is going to be much, much stronger than if you have similar non-polar molecules. Now, keep in mind, polar molecules also have London dispersion. It's just, so they have 2 types of forces, if you will, except it's just not as strong as the dipole-dipoles are. Right? So it's kind of like look for the strongest one, and the dipole-dipoles win. Okay, number 3 on the list of van der Waals type forces are hydrogen bonds. Right? Hydrogen bonds are the strongest. Again, we're talking from one molecule to the next, right? Attraction. First of all, the word bond, hydrogen bond, horrible name. I think they're probably named that way because it reminds people of genuinely true bonds, a covalent and ionic bonds, because they're so darn strong. They've got such a high value of energy to them, but they're not bonds. Right? Bonds are within one molecule, holding an atom to another atom to another atom to make that molecule. We're talking about intermolecular forces between 2 different molecules, right? There's no bonds between those. Right? So the name is unfortunately poor. They're not bonds. Right? All right. So what are they then? Well, hydrogen bonds are actually a special case of dipole-dipoles, which we just talked about. Permanent dipole-dipoles, but they're incredibly strong ones. The rules for hydrogen bonds are you must have a hydrogen connected directly to either a nitrogen, an oxygen, or a fluorine. You must have that somewhere in your molecule. If you don't have that in the molecule, then you don't have H bonds. It's that simple. All right? And so you can rule it out pretty easily, or you can include it fairly easily too. But you got to know the structure and what's connected to what, of course, in your molecule. Right? Now notice N, O, and F, if you look at the periodic table, N, O, and F, they're right, the three elements at the very top right corner of they're like the strongest electronegative atoms and the smallest, strongest, highest electronegativity atoms out there. And because of their small size and their high electronegativity, the dipoles that they form are particularly large. So it's a partial positive, it's a partial negative, but it's a big dipole, bigger than the typical ones that are formed from polar molecules. And so they're going to have especially strong ones. And also, again, because of the small size of both the nitrogen, oxygen, fluorine, and the hydrogen, these dipoles can actually get very, very close together, which again strengthens the attraction that they're going to feel. All right, so they're very, very strong dipoles, and that's the key there. Here's a picture that I drew of two water molecules. Notice water does have an H directly connected to an oxygen. So as soon as I see that, I know water is going to have H bonds. Now to get an H bond, of course, I've got to draw a second molecule and see how does that look. Now the dipole here, let me draw this here in maybe green. Here we go. This is the partial negative side because the oxygen is more electronegative, and so the dipole is going this way, right? Just for that one bond. Overall, the whole molecule has one going straight up through the oxygen. But that one bond there, the H to O bond, there's the dipole. So you got this fairly strong partial positive right there. The next molecule over, this water, again, there's its partial negative. And so, hey, those two partials are going to attract to each other. I drew that with the dots, the red dots there. That's your H bond. Okay. Now, one thing to notice, let me just take those back off that I just drew. One thing to notice that H bonds are, like I said, fairly close together. They're very strong, and they like to be linear. And if I can draw a box around the atoms that are involved here in this H bond, it would look like that. 180 degrees straight across from the OH bond of the one to the O of the other. That's the H bond. Now you can form H bonds where they're sometimes a little crooked. Yeah, that does happen, but they're just not quite as strong. They will try to arrange themselves in a way to make that a linear H bond if at all possible, because that's the most stable conformation and it is the strongest attraction. H bonds can describe trends like are shown in this figure from the textbook. This figure, take the blue line for example. The blue line is, let's see, H2Te, that's the molecule, H2Se, so dihydrogen tellurium, dihydrogen selenium, dihydrogen sulfide, and then dihydrogen oxide or water up there. And we're looking at the boiling point. The boiling point of these, and again the period, in other words, we're going down. So here's oxygen, sulfur, selenium, tellurium. So we're talking about this column right here. Of course, they're in the same column, so we have similar chemistries. If we can form H2O, then we can form H2S and H2Se, etc., etc. As we go down, of course, these get bigger, very much larger in size. And so if I start with the sulfur as a starting point, I actually start over here, Te. All right. That's a very large atom. Because all of them have dispersion forces, right, it's going to have those London dispersions connecting one H2Te to the other. Right? And so I get a certain boiling point. Right? They're not very polar, truthfully. If you look at the electronegativity difference between an H and a Te, it's small. Okay? H2Se, Se is not as large of a molecule. Again, on the periodic table, I'm starting with Te and I'm going up, right? So I'm getting smaller and smaller molecules as I go across here. So it's smaller, doesn't have as much contact, doesn't have as much electrons, so the dispersion forces are less, which means it's easier to boil it. So its boiling point goes down. It's easier to rip those things apart. I don't have to get them as hot. Go to sulfur, down even further. And this trend makes total sense when you think about it in terms of London dispersion forces. But then all of a sudden, the smallest one yet, the oxygen, all of a sudden, huge jump. Way up, way above where the Te started at, right? Way, way up there. You say, wait a second, this is the smallest one, it has the fewest electrons, it has the fewest surface, the smallest surface area of contact. Why does it jump up huge? Why does it have very large attractive forces between it? The answer is actually twofold. Number one, the HO bond is the most polar out of all of these, and so you get these dipole-dipole interactions, but more specifically, it's that special kind of dipole-dipole. It's got the H connected directly to the O. It's an H bond, and H bonds are very, very strong. Right? This has H bonds, none of the other three do. So these are following the trend that we would expect, going down, 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 and then all of a sudden it shoots way, way up because we have very strong H bonds connecting it, so you got to heat that up a whole lot to get those to come apart and get the thing to boil. We see exactly the same trend with HF, HCl, HBr, and HI, the halogens, or ammonia, NH3, PH3. The same trend holds for all of them. Now, interestingly, they don't show this on this chart, but what if we did it with the carbon, silicon, germanium, and tin line? Well, if I was to draw that, the tin is the biggest, and so I would expect the tin would be H4, if you will, tin. Next would be the GE, H4, and then the SI, H4. It would be going down, 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 just as I go from the largest to the smaller, and when I got to carbon, whoop, it would be way down here. It would continue that downward trend because there are no H's connected to O, N's, or F. That is to say, there are no H bonds that kick in. And so those would follow the normal trend due to London dispersions. It's just these three right here that break the trend because they have H bonds. H bonds are really, really important in a lot of molecules. They're very, very important in biochemistry. DNA, for example, has the double helix ladder connecting the left to the right side are H bonds. Right? And so if you think about the structure of DNA, that backbone, the side of the ladder, if you will, is made up of a phosphate followed by a ribose sugar. That's what. Here's your phosphate. You guys know phosphate, PO4 3 minus, right? And then this is a ribose sugar, another phosphate, another ribose. To keep on going down, just alternating back and forth, back and forth. Here's the other side of the ladder, phosphate and sugar, phosphate, sugar, going up and down like that. And then you've got the rungs of the ladder. Let's do that in green. Here's the rungs of the ladder right here, and then right here, and it would continue on forward. Okay. So let me actually erase those rungs for a second. All right. If you look at what those rungs are made of, what are the steps of the ladder made of? You have 4 different bases: thymine, adenine, guanine, and cytosine. To connect those bases from the one side to the other side are H bonds. If you look at this, I've got an O over here, and I've got an H2N. So here's my H connected to a nitrogen on this side. And then here's an oxygen over on this side. And they're going to H bond then because I've got everything I need. I got an H connected to an O, N, or F. And on the second molecule, I have an O, N, or an F. And so I form the H bond going across from one to the other. Here, the second one between adenine and thymine, again, an H connected to an N and an N over here. Right, so here's my next H bond. Between a cytosine and guanine, their geometries, the shapes of those line up, so they actually get 3 H bonds that form. And so DNA is held together by very strong H bonds. But they're not as strong as true covalent or ionic bonds, and you can, given the right energy levels or the right enzymes in the cell, you can get those to come apart. You can unzip it. They call that the DNA melting, if you will. And if you think about it, if you've got a DNA that's composed of a whole bunch of thymines and adenines, they're held by 2 H bonds each, 2, 2, 2, 2 if you had a whole bunch of them. If you have DNA with a whole bunch of guanines and cytosines, that has 3 H bonds, so 3, 3, 3 going on down. That is going to have a much higher melting point. That is to say, it's going to take a lot more temperature, a lot more energy to pull those 2 strands of DNA apart than if you had a bunch of AT rungs DNA base pairs. So the actual composition of DNA can be determined by looking at what temperature do I have to heat this up to get those guys to separate. It's all due to intermolecular forces, in particular all due to H bonds. Alright, so we'll end this section here by looking at example 3. They give us 3 molecules: dimethyl ether, ethanol, and propane. They say, hey, there's 3 boiling points: negative 42.1 Celsius, negative 24.8 Celsius, and negative or positive 78.4 Celsius. Match the molecule to the boiling point. Well, the higher boiling points are going to correspond to the molecules that are harder to rip apart. That is to say, they have stronger forces, stronger intermolecular forces. The lowest boiling point, hey, it didn't have to heat it up very much to get that thing to boil, so they must have fairly weak forces. So I have to look at it and ask myself what kind of intermolecular forces are in each one. If I think about the first one here, right, well, CH3, those are all nonpolar, CH3 nonpolar. Our CO bond is polar. So this one, as all molecules have London dispersion forces, and it also has dipole-dipole type forces. The middle one here, ethanol, everybody has London. But then this also has an OH, an H directly connected to an O. Hey, that means this has H bonds as well. That's that special kind of dipole-dipoles, right? The third one, propane, I don't see any OHs or NHs or that. I don't see any dipoles. It's all nonpolar. The only one this one has is London. Okay. Notice this one does have both hydrogens and oxygens, but they're not directly connected. If I was to draw the structure of that out, I'd have a C with the 3 H's, then it's bonded to an O, to the next C with its 3 H's. So it's got both hydrogens and oxygen, but I don't have an oxygen directly connected to a hydrogen like that. I don't have that. If I did, I'd have H bonds. That's what happens right here in the ethanol. For this top one, nope, don't have it. I've got dipoles, but I don't have H bonds. All right, so I look at the forces that are involved right there that I have, and I think it's pretty clear that this one with only London forces doesn't hold those very strongly together. So it's going to have the lowest. And so that one right here, my propane, is going to be the lowest one right there. That's going to be the negative 42.1 degrees Celsius. You don't have to get it very hot to get that thing to boil. And, you know, if you think about it, propane, that is a gas at room temperature. You know, you get your propane tanks for your barbecue grill, that's a gas coming out there. All right, the ethanol, that's the strongest because it's got those big, strong H bonds. And so my ethanol, I would attach it to the strongest one. So that has to be the 78 one. You got to heat it up pretty hot. And ethanol, yeah, that's the alcohol that's in beer and wine. That's a liquid, isn't it? A liquid. Dimethyl ether, that one's right in the middle, and so its boiling point is the negative 24.8. It's also a gas, but again, you have to heat it up a little bit more to get it to be a gas at room temperature. Negative 24. Propane, you only had to get it up to negative 42 before it turned into a gas.